All right, so our speaker today is Dr. Hanye Zhu. So Hanye got a PhD degree in 2024, last year, and now he's a postdoc at Duke University. So his title today is Field Concentration for the Conductivity Problem of Closely Spaced Perfect Conductors with Imperfect Bonding Interfaces. Hanye.
Thank you, Hongjie, for the introduction and the invitation. It's my great pleasure great honor to speak at this online seminar. So my topic today is based on joint work with Hongjie and Zhuolun on the field concentration phenomena for the conductivity problem. Can you see my screen properly? I think. So this is a outline of my talk today. First, I would describe some physical background and describe some literature in the setting of perfect bonding interface. And next, we will discuss a few results from our recent work on the imperfect bonding interface. And finally, we'll give some open problems. So first, the physical background. So a key feature for the composite material is a combination of fibers or called inclusions and a matrix which is also called background, which have different physical properties. This is a key feature. And the phenomena of field concentration is that if two inclusions within a composite material are positioned very closely to each other, and their material property significantly differ from the background matrix, then it will lead to a significant buildup of certain physical quantities, such as stress or field intensity in the narrow gap between those inclusions. So this is a physical phenomena. And if this phenomenon becomes studied in a study of effective medium theory, so this picture is what I have taken from Killer's paper. So basically, this paper says if those size of the inclusions is how to say, if the gap between those inclusions is small enough compared to the size of the inclusions, then the classical effective medium theory does not work very well. So, and that phenomena leads to the analysis of this field concentration phenomena. However, the field concentration phenomena is kind of a double-edged sword. In one hand, it can cause certain material failure because of significant buildup of a certain physical quantity, which can lead to the failure of a material. But on the other hand, people also use this phenomenon to customize some enhancement of certain field. I mean, from my knowledge, there's some work in biology and also medical treatment. So let's then talk about the mathematical configuration. So because the phenomena is only happening in between the narrow region between the inclusions, So we are only looking at two inclusions as a model. So here, this D1 and D2 are the inclusions, which has the distance between them is denoted by epsilon, which is quite small, and compared to the diameter of those inclusions. And we also assume the distance from the boundary to the inclusions to be unit size. So as I already said, the most interesting behavior only happen in between the narrow region, like this neck region. So the governing equations for the problem, I mean, there are certain different contexts, but let me use the electroconductivity problem, for example. So in that problem, U is the voltage potential, and E, which is a minus gradient U, is the electric field, and J is the current, sigma is the conductivity, and we have the Ohm's law, which is J equal to sigma E, namely the current is proportional to the electric field. And we also have the Kirchhoff's law, which is the divergence of the current is zero. So from those governing laws, if we assume a continuity of potential and continuity of flux across the interface, namely the partial D1 and partial D2, we have those equations, then this will lead to the classical problem, conductivity problem, modeled by the following elliptic equation. So the key feature here is this equation is still a divergence from elliptic equation, but the coefficient is piecewise constant in those different regions. So sigma k is k equal to k inside those inclusions D1 and D2, and 1 in the background matrix, which we denote by omega tilde. Okay. And as I just mentioned, the electric field Ek is a gradient of Uk, which denotes the electric field. So basically, an interesting question is to estimate the electric field, namely the gradient of the solution to this equation. And mathematically, it is also interesting because from the classical theory of elliptic equations, from the de Giorgi-Matsumoto theory, one can only get Holder continuity for the solution. So we want more precise description of the regularity estimate. Namely, here is physical quantity of the gradient of the solution. Okay. So in the literature, when this K is bounded, uniformly bounded, is bounded both from below and above, independent of epsilon, then the gradient is shown to be uniformly bounded independent of epsilon. So this was first discovered, observed numerically by Babuska et al., and later proved by Bonetier-Vergelius for 2D circular inclusions, which are touching, namely when epsilon is 0. And after that, Lee and Vergelius proved this result for general inclusions in any dimensions and any distance between the inclusions. And Lee and Nirenberg generalized this boundedness result to elliptic system, including the system of elasticity, which is the system for the stress. So, however, when this the conductivity of the inclusions K go to infinity or zero, there's also a lot of numerical evidence that suggests the gradient can be unbounded when epsilon goes to zero. This is the phenomenon of field concentration. So we know the field concentration phenomenon can only happen when we have extreme conductivities. So let's look at the limiting case. First, when K goes to infinity, the solution will actually converge to the solution of the following equation. So here we have the Laplace equation in the background matrix, and we have the solution equal to some constant in those two inclusions, with these constants a priori unknown, but can be determined by this third zero flux condition on those boundaries, on those interface boundaries. And we have another boundary condition on the outer boundary, partial omega. Okay. So this can be seen maybe from the variational formulation of the conductivity problem, where the solution UK is actually a minimizer of the potential, and as you can see here, if K goes to infinity, the solution can only be du can only be zero inside those inclusions, because sigma K is infinity. So there are a lot of work on this perfect conductivity problem. I'm only mentioning a few for the blow-up rate of the gradient. So based on the work by American Lin, and Yun and Baoli Yin, the blow-up rate is shown to be epsilon minus 1/2 in 2 dimensions. However, based on work by Baoli and Yin, it is the blow-up rate is actually epsilon log epsilon to minus 1 for 3 dimensions, and epsilon minus 1 for higher than or even equal to 4 dimensions. So all the exponents here are optimal in the sense that there are examples where those upper bound can actually be achieved. So when another limiting case is when K goes to 0. In that case, this solution UK will converge to the solution of the following, we call it insulated conductivity problem. So in this equation, we still have the Laplace equation in omega theta. However, we will have Neumann boundary conditions on those inclusion boundaries. So people may think this equation is simpler compared to the perfect conductivity problem. But in my opinion, this problem is actually much harder than the perfect conductivity problem because of the squeezing effect of those inclusions. So basically, in this situation, because of the second Neumann boundary condition, the field will be squeezed in between the inclusions. So actually, the blow-up rate is depending on the principal curvature of those inclusions. So they are relatively more slower progress on this problem. First of all, in 2 dimensions, this problem is actually the dual problem of the perfect conductivity problem by harmonic conjugate argument, because this condition, this Neumann condition, is harmonic dual for the tangential derivative to be 0. Okay. So based on this argument, in 2D, the blow-up rate is still epsilon to the -1/2. Okay. And later, Baoli and Yin give the upper bound for the gradient of the same order for higher dimensions, but people do not know whether this is optimal or not. And 6 years later, Yun gives an example, which is 2 spherical inclusions, and the blow-up rate of the gradient is actually this number on the shortest line between those inclusions. Okay, so this number, this exponent, is larger than -1/2, which may lead to people to think maybe there is a better blow-up rate. So later, Li and Yang gives an upper bound for the upper bound for the gradient of this order epsilon -1/2 plus some positive number beta. But this beta is implicit at that time, and Wenkov gave some characterization for the beta, but it's still not optimal at that time. And finally, the optimal value of beta is given, is obtained by Dongli and Yang and Li and Zhao in the quite recent works in higher dimensions, where this value beta is depending on the, as I just said, depending on the principal curvatures of those inclusions. So any questions on the literature? Okay. So now let's talk about the imperfect boundary interface case. Okay. So this is boundary conditions, interface boundary conditions proposed by physicists and biologists, where we consider these inclusions to have such a membrane structure, which is a coherent structure, where you have different conductivities for the core and the shell. And as usual, we will denote we will set the conductivity of the background matrix to be 1 by just the scaling. So we send the thickness of the shell to be 0, to go to 0, as in the membrane structure. So if this limit Ks over T exists, then this is called the LC type interface condition. And this leads to the continuity of flux. However, there's no continuity of potential. This is called the LC type bonding interfaces. There's also another type of bonding interface called the HC type, where you do have the continuity of potential, but you do not have the continuity of flux. So a key feature here in this structure is that this Ks will always be very small because we assume this limit to exist. So Ks is small. You can kind of consider it as you're cloaking, you're gluing a insulating layer, infinitesimal layer on this inclusion. So there are a lot of physical literature on this model because in real life you always have contact resistance due to roughness or debonding at the interface, and this will actually lead to a lot of interesting interfacial effects. So we're still looking at the limiting case when the conductivity of the core is infinity. Then, I mean, this model is kind of, this is infinity, this is 0, and the outside is 1. Then this problem, this equation becomes the following. Well, we still have the Laplace equation in the background matrix, but we have this type of Robin boundary condition on those inclusion boundaries with the 0 flux on those inclusion boundaries. And here Uj is some, it's also some constant determined by those 0 flux conditions. So actually this model, this setting corresponding to a physical situation where some metallical particles are embedded in the epoxy matrices, where in this physical situation, the interfacial resistance is capacitance type, where physics can actually measure and compute. So our work is motivated by this recent work of Fukushima, Ji, Kang, and Lee. They show that if D1 and D2 are unit disks in 2D, and if omega is just the whole space, and phi, the boundary condition phi to be, sorry, this is not xn, this is x2, then the gradient is actually uniformly bounded independent of epsilon. So The reason why this is interesting is that in the perfect conductivity problem with perfect interface, where you just, where in the equation you just erase this term. So for that equation, the gradient will blow up under this boundary condition. So in that case, du is actually of order epsilon minus 1/2. So this kind of imperfect interface will lead to a suppression of blow. So we are interested in more general inclusions and more general dimensions and more general boundary conditions. So this is yeah. So before going to the rigorous results, let me just first do a comparison of the phenomenon with perfect or imperfect bounding interface. So we assume for the simplicity, D1 and D2 are two balls centered at the xn axis. And we choose omega to be a larger ball containing those balls. Okay. And U to be phi on the boundary of omega. So from previous literature, for the perfect interface case, where the potential and the flux are both assumed to be continuous across the bounding interface, then it was proved first that if K is bounded from below and above, du is always uniformly bounded independent of epsilon. And also, if K is infinity, this is a perfect conductivity problem. When in this case, when phi is in the xn direction, so if phi is xn, then the gradient of u is the order of epsilon minus 1/2 in 2 dimensions, and epsilon log epsilon minus 1 in 3 dimensions. Maybe this is absolute value. And however, in the insulating case, when k is equal to 0, and the boundary condition is in the tangential direction, the horizontal direction, say phi is equal to x1, then the gradient is of the scale epsilon minus 1/2 in 2D, but it is in the scale of epsilon square root of 2 minus 2 over 2 in 3D. Okay. So this is a review of previous literature. So what we have done is we proved a few optimal blow-up rate in the imperfect bonding case. So as I just introduced, we consider the LC type problem, where we assume the potential, we assume the flux to be continuous across the interface, but the potential can be discontinuous. And we consider the limit case when k is equal to infinity, namely the conductivity of core to be infinity. So we have a perfect conducting core with kind of insulating shell. So in this case, if this gamma, if for any gamma, if phi is in the xn direction, then we can show that the gradient is uniformly bounded independent of epsilon. So this is a generalization of the previous work I mentioned by Fukushima, Ji, Kang. However, if the boundary condition is in the x1 direction, we have shown that there's actually a dichotomy happening here, that if gamma is below this critical value r, and phi is x1, then the gradient is uniformly bounded. However, if phi is above this critical value, then this the gradient will blow up, and we can characterize the optimal blow up rate in 2D and 3D, and actually in any dimensions. But I'm just giving just showing these numbers, and actually can compare those between those exponents in the perfect case. So as you can see here, so when gamma goes to infinity, this exponent will converge to the exponent for the insulated conductivity problem. So basically that means in terms of the field concentration phenomena, those inclusions will actually behave like two insulators, even if the core of the inclusion is perfect conducting. Okay. And in the case when gamma is equal to r, which is a critical case, you get 0 for those exponents, and this case is actually corresponding to a physically interesting critical case where the insertion of such inclusions will not perturb uniform field. So basically that means if you initially have a uniform field in some direction, you insert those inclusions, the field will still be uniform outside those inclusions. Okay. And in other words, it's a kind of a cloaking, because it's kind of, you cannot detect those inclusions using uniform field. Okay. Okay. Any questions about our version of our results? Okay. So no questions. Let's give the rigorous results. So this is still the domain of interest, which is a narrow region in between those inclusions. And actually still by maximum principle and classical gradient estimate, we know U is bounded, and those constant U1 and U2 are also bounded. And the gradient is also uniformly bounded outside those shaded region, where the horizontal scale is 1. Okay. So because we are interested in this narrow region, we zoom in, and the interfacial boundaries will look like this. And we construct the coordinates correspondingly. Basically, those are graphs of some functions f and g, and we assume those functions to be C11 satisfying those conditions, namely those interfacial boundaries to be relatively convex. And importantly, we denote this cylindrical region, okay, to be omega x naught r, which is useful for our discussion later. Okay, so we can kind of first constrain to the local problem near the origin, where you have a Laplace equation with just constant Robin boundary conditions on the upper and lower boundaries. So our first result shows that the gradient, you have this kind of upper bound for the gradient, which is crucial anisotropic gradient estimate. We will use lots of times. The crucial thing here is even this estimate, you can see this is epsilon minus 1/2. So even in this estimate, it is different from the perfect interface case, where the blow-up rate is it's possible it could be epsilon minus 1 in higher dimensions and epsilon log epsilon in 3 dimensions. So this estimate we get actually excluded those possibilities. So I will postpone the proof of this estimate to the end, and let's see what we can get from this crucial estimate. So as a corollary, which is the first result I just showed, is that if this omega theta is symmetric with respect to xn and phase of odd function xn, then the solution is always have a uniform bounded gradient. So the proof is actually not quite difficult using the crucial estimate, because by the symmetry and uniqueness, we know U1 is minus U2 equal to minus U2, and the solution is 0 on the x-axis, x prime axis, x prime plane. Then by the estimate and the maximum principle, first we can get this estimate. And however, by the mean value theorem, we know for any point, we can write it as it's always bounded by derivative times the xn coordinate, because this part is 0. However, this xn behaves like r squared, because for the picture, this is r, this is r squared. So you have a gain of exponent r, and you plug in back into this estimate, then you get uniform boundedness. And next, we can prove that if this gamma is sufficiently small, then you have a uniform bounded gradient. And moreover, there's actually a decay, polynomial decay, if U1 and U2 are equal. And this, the proof of this theorem is based on iteration of the energy estimate and applying the previously mentioned anisotropic gradient estimate. So next, we consider this kind of radially symmetric case. And we assume the domain to be symmetric with respect to xj, where xj is just some horizontal direction, and the boundary data phi to be odd in xj. So in this case, by symmetry and uniqueness, the solution is actually odd in xj and satisfies this homogeneous problem, where uj's are 0. Okay. So in this case, we can actually show if gamma is less than 1 over mu, we have uniformly boundedness for the problem. However, when gamma is greater than this number, then the gradient we have the optimal plot rate for the gradient, where the rate is given in this formula. This is quite similar to the insulated conductivity problem with a perfect interface. And this exponent is actually optimal in the sense that we have an example which has achieved this the same lower bound. And the idea of proof is first actually by the anisotropic gradient estimate, the derivative in the xn direction is actually bounded on the interfacial boundaries. So by using maximum principle, actually you can prove it is the vertical derivative is actually bounded inside the cylindrical region, inside the narrow region. So we, instead of studying the original problem, we can study the equation for this average in the xn direction, which lead to this equation, and we can obtain estimate for this equation, which is an equation in a quite regular domain in Rn-1. Although the equation is more difficult because the coefficient is maybe can be degenerate. However, there's certain ways we can do to treat this problem. Okay. And yeah, so that is all the main results. So any questions? Okay. So if there are no questions, let me briefly mention the proof of this crucial anisotropic gradient estimate. Oh, sorry, this R. As I have already mentioned, for this cylinder, omega xr, every point in this cylindrical region, we have the comparable height. That is the reason why this estimate can work. So let me give the outline of the proof. First, we can assume U1 to be negative U2 and F and G to be, well, we assume it to be smooth, but if it is not, we need to do a lot of other modification stuff. We also fix point and prove the estimate at that point. And this is a crucial observation I just mentioned. And next we do a flatten. So basically, we'll flatten the interfacial boundaries. However, we want to preserve the normal directions on the interfacial boundaries. Okay? So basically, on here, you have the same. So we define the map reversely by this. Well, if you forget about this term, this is just the usual flattening map, where you just do a flattening of each vertical line by just doing a scaling. However, here, because we want to preserve the normal direction, we add this H term, and it will actually lead to this kind of deformation. Okay, but it will preserve the. Maybe I did it the wrong way. But it will preserve the Neumann direction, the normal direction on the boundaries. So here, we put the answer to be this, and we just solve theta and zeta by assuming zero, by assuming the map preserve Neumann, preserve normal direction. Okay. So after the flattening, the solution actually becomes a solution of the following problem, where we have this non-divergent form second order elliptic equation inside this this cylindrical region, and we still have roaming boundary conditions on those upper and lower boundaries. The reason we can get these boundary conditions is that we prescribe the normal direction to be preserved, and we can actually estimate some estimate for this coefficient. Importantly, is this gradient of A is not too bad. Okay, and A is bounded from below and above, because we are looking at the radian of scale square root of epsilon. Okay, so and this F1 and F2 are just here. Okay. And after that, we want to reduce the problem to homogeneous Robin boundary condition. So we take this answer of function linear in Yn, and we assume it to satisfy the same Robin boundary conditions as U. So because of this, the difference V of U tilde and the W will satisfy the homogeneous Robin boundary condition. But because we have a forcing term on the right-hand side, however, the forcing term, we can actually get a good control, namely the second order derivative is bounded by 1 over R. Okay. So after that, we will reduce the problem to homogeneous non-human boundary conditions. Okay. We take this V tilde to be this E2 phi times the original V, where this phi to be satisfy to be this answers. Well, because of this chain rule, if this phi satisfies those two conditions, then this V tilde will satisfy the homogeneous non-human boundary condition on the upper and lower boundaries. Okay. So by introducing this transformation, we introduce other terms. Okay. However, those terms we can get a good control. And next, right? Because right now we have a second order elliptic equation with non-human boundary condition. We can do an extension. Right? We can basically do an even extension with respect to those two boundaries, and we do periodic extensions. Then the solution will become a solution to still to a elliptic problem in the infinite cylinder. However, you need to do kind of the corresponding extensions for the coefficients, namely even extension for Aj, An, Bi, and C, and H. However, all the extension of Ain, Ani. Okay, so an interesting thing here is that those two order extensions, Ain and Ani, are actually still continuous on those boundaries, because we can actually show this Ain and Ani is actually 0 on those interfacial boundaries. Okay. Then by using the classical W1P estimate and some embedding and rescaling argument, one can actually show, using the previous estimate on the coefficient, that this estimate on the V tilde will hold, and after substitution backward, we get the anisotropic gradient estimate in U. Okay. That is the outline of the proof. And of course, because of lack of regularity, we need to do a lot of modifications in those kind of formula argument. For instance, because we want the d squared of b to be continuous, So we need lots of modification arguments. Okay. So a few remarks for some open problems. So we consider the case when the connectivity of the core is infinity. So well, another interesting problem is when the conductivity of the core is finite, right? So remember in the membrane structure, what our result shows is that if the core is infinite, but if gamma is sufficiently large, the inclusions will still behave like insulator, right? So one should expect maybe in the finite case, the inclusions will also behave like insulators, right? But there's up to now we don't have rigorous proof for that. Okay, and also there are certain questions on the HC type problem, and also unified estimate with precise dependence on those parameters, say the conductivity, distance, and the bonding parameter. And also, because if you want to some practical use, there's also interesting question on how to design numerical method to precisely compute the gradient with rigorous error estimate, uniformly absolute. And also, systems is quite at the early stage, and I'm also interested in other contexts, because in this case, a little bit imperfect interface will lead to a behavioral difference for the connectivity problem. And I think that's the end of my talk. Thank you for your attention, and I'm happy to answer questions.
Thank you, Hanye. Any questions from the audience?
Yeah, I have two questions on the main sort of estimates, the main theorem that you guys have. I mean, they are mostly academic because I don't, just basically when you have like the two boundary condition are constant U1 and U2, right? If you replace them by functions, because I imagine that you go from U1 to U2, if the difference is not homogeneous, then what happens? I mean, let's just replace constant by functions. U1 and U2.
You mean
Yes.
here?
Yeah.
Yeah, I think that we have some quite recent work on that, and I think it's not quite different.
Okay.
We still have the similar estimate here. Yeah.
Okay. And then the second question is that what if you replace the Laplace operator by a general, more divergent or non-divergent form elliptic operator?
Yeah, that's a good question. I think for this anisotropic estimate, it will still work, in my opinion. Yeah, but for other estimates, because for other result, because they use some certain symmetry, I think you really need some symmetry on the coefficient for those results based on our approach.
Yeah, thank you.
Other questions? Okay, so if no questions, let's thank the speaker again.
Thank you.
Thank you.
Let me stop